So the idea is discussed here. It's the same way. So as you see here, if we are getting uh, less than two integrator, so with two integrator, we are going to get finite. Less than two integrator, we are going to get the error equal to infinity. Infinity means it's not acceptable. Let us look at this example. In this example, he's saying find the steady state error for the input of 5 ut, 5t ut, 5t square ut, which 5 unit step, 5 unit ramp, and this parabolic input. Let us look at the transfer function. The system, first of all, is unity feedback, where what is given here is the open loop transfer function. That's one thing to be noticed at the beginning. So I realized that we are going to get the formulas which just calculated. And beside that, I found that there is no integrator here, no integrator. Okay, if there is no integrator, I know before we start that without integrator, if the input is step, we are going to get the error as a finite value. That we know before we start. Let us calculate now. So the input is 5 over s. The formula to calculate the steady state error, if the input is step, is this one. So now we are going to substitute the value of gs. So by substituting the value of gs, it's equal here. If I put it's 5 over 1 plus the limit of gs, if you replace this one by gs, which equal to 120 into s plus 2 over s plus 3 into s plus 4. Of course, s is 0, which means it's going to be 120 into 2, which 240 over 3 into 4, 12. 240 over 12 equal to 10. 240 over 12 equal to 20, sorry. So this is 2, 0, and here 1. So it's equal to 20. That means the limit is equal to 20. A plus 1 is a 21. That means it's equal to, yeah, it's here. Sorry, I didn't see it, but here. It's 5 over 1 plus 240 over 12, which equal to 5 over 21. That means the error is finite. Finite means certain value. When I say the error is finite, means certain value, which found to be 5 over 21. How about for the ramp? For the ramp input, if the case is ramp, we will substitute and we will calculate, though we know the answer before we proceed. We know the answer before we proceed, because here we are having no integrator. So if the input is ramp, we are going to get by the end of the day infinite error. Similarly for the parabolic. For the parabolic also we are going to get infinite error. Okay? Let us look at this example now. This example is similar to the previous example, except we are having here one integrator. So I think it's very clear now. Before I start the calculation, I know that this will give me 0 error. This will give me finite error. This will give me infinite error. So if you are in real exam, no need to calculate the detail. Only this value to be calculated. Only this value to be calculated. Because this one give me the answer of 0. This give me the answer of infinity. I know. Let us calculate and see. So for 5 ut, we are substituting in the equation as before. We find that it's 5 over 1 plus infinity because of the integrator. The integrator here going to give me 0 in the denominator, which result in infinity here. 5 over infinity equal to 0. Done. Now for the second one, when it's ramp, I know that the answer is finite. Let us see. S into 5 over s square over 1 plus this value. When you substitute, you will find the result is finite value, certain value, which 1 over 20. Similarly for 5t square ut, when we convert it to Laplace, it's equal to 10 over s cube. In Laplace, this value, in Laplace, it's equal to 10 over s cube. S will cancel s cube, the remaining will be s square. S square will come to the denominator, and we will calculate to find finally it's equal to infinity. The error will be infinity. So my dears, you don't need to calculate the detail here. The only value to be calculated, if you understand what we mentioned earlier is this value. Other than this, we know this is 0 and we know this is infinity. So here are the formulas given. He gave me the formula for input equal to this. For ramp, it's this one. For parabolic, it's this one. These are the formulas needed to calculate the error for different inputs. Remember that here it's 1 over limit of s into gs. Here s squared into gs. Okay, now this gives or can help us to catch certain point that these values are going to be a constant which will decide something in the function. So we are giving them with names. We are going to assume that Kp is equal to the limit of gs, which is this value. Let me just erase it first. This value, we will give a name for it as Kp. And this value, we will give a name for it as Kv. This value, we will give a name for it as Ka. We call this one position constant, and this is velocity constant. This is acceleration constant. Of course, sometimes we can rewrite these equations. I think it's shown in the next slide. This is going to be or can be written as a 1 over 1 plus Kp. This can be written as a 1 over Kv, and this can be written as a 1 over Ka. Okay, for the system shown, find the static error constant and find the expected error for the standard step and ramp inputs. So we need to calculate the constants. We'll start by Kp. Kp is equal to, you see here, it's the limit of gs, which is going to be finite because there is no integrator. I think this is clear. But when I calculate Kv, I found that Kv equal to 0 and Ka equal to 0. Now, if I want to calculate the error is here. This is 1 over 1 plus Kp, which equal to finite. Actually, I know that it's finite. We know before we start because there is no integrator in GS, so the answer will be finite value. And when the input is ramp, you will find that, or we found that Kv equal to 0, which means the error equal to infinity. Similarly, for the parabolic, Ka equal to 0, which gives me the error of infinity. Look at this example again. For this case, similar to the previous case, except we are having here one integrator. So I think now we can guess of what are the constants, the value of the constants, and the value of the error. The constant Kp will be infinity. The constant Kv will be finite because we have integrator. We have integrator here. So Kv will give me finite value. When we substitute, when we find the limit of this function, this s will cancel this s. The remaining will be 500 multiplied into 2 multiplied into 5 multiplied into 6 divided by 12 into 10 into 8, which give this value. How about Ka? When we are having here s squared, this is going to result on Ka equal to 0. How about the error? We know before I start calculation that the error for the first case is equal to 0 because we are having one integrator. And for the second one, we know that it's finite value because it's having one integrator. And for this one, it's infinite because it's having less than two integrators. One integrator. Type of the system, we are going to classify the systems as a types. And the type will be based on the power of, the number of integrator. The number of integrator is representing the system type. Means what? Look here, this is the system, and this is GS, where in GS we are having s to the power n. If we have n equal to 0, that means there is no integrator. If n equal to 0, no integrator. N equal to 1, we have one integrator. N equal to 2, we have two integrators. So the classification of the system based on this point. If there is no integrator, we will call the system type 0. No integrator, system will be type 0. one integrator system will be type 1, two integrator system will be type 2. That's how we can figure out the system type. Look here, when n equal to 0, system is type 0. When n equal to 1, the system is type 1. You see here, we are having no integrator. One integrator, two integrator will be type 2. This is just a conclusion of what we mentioned so far. We gather everything. We are having here, for example, I will take the first column just to check what's happening. If the input is a step, the steady state error can be calculated by this formula. And when the system is type 0, that means there is no integrator, we will calculate the static error, the constant, the static error constant can be constant value. It's going to be constant value, which giving me the error equal to constant can be calculated using this formula. In the same time, if I calculate the Kp, if I calculate it, it's equal to infinity, which will give me the error of zero error, because we will have more than one integrator. I mean, one integrator or more. One integrator or more, that means the error will be 0. Similarly for type 2. Type 2 means we are having two integrator. If two integrator, that means Kp is infinity and the error equal to 0. You can think the same way on the other cases. Okay, let us consider this example. In this example, he's saying a unity feedback system has the following forward transfer function, gs equal to so and so. I want you to get clear about the question. Let's look at the system first of all. The system is something like this. This is the system which called unity feedback system. With this is plus and this is minus. What is the meaning of unity feedback? Because this line is unity. There is no transfer function. It's only one. That's why we call it unity feedback. The other point, when he say the feed forward transfer function, this one, he means this block. This is called feed forward transfer function, which gs equal to this value. If the case is like this, he said, we want to evaluate Kp, Kv, and Ka with the system type. Also, we want the system type. First of all, I will look at the number of integrator available here. How many integrator? 0, no integrator. That means the system is type 0. When the system is type 0, I'm expecting Kp to be finite, and I'm expecting the error due to step will be finite. Let us start with the constant. So with the constant, when I calculate Kp, it's a finite. So we will apply the limit. The limit of gs equal to what to say, 1000 into 8 over 7 into 9, which equal to 127. So you see, Kp equal to finite value. That's because no integrator. How about the other two constants, Kv and Ka? They are going to be 0 and 0. Because there will be s, if you remember, there will be s in the limit. So it's for this one, for example, it's the limit of s into gs. So when you put this gs here, s will not be removed. So s will destroy, let's say, the function. So the result will be 0. Similarly here, it's equal to 0. For the other part, b, he want to calculate the error. The error for the step is 1 over 1 plus Kp. That means 1 over 1 plus 127, which equal to 1 over 128, equal to this value. I know that it's finite, and this is the value. For the other two, it's 1 over 0, 1 over 0, which infinity, infinity. Interpreting the steady-state error specification. What he want to tell us here, he said what information is contained in the specification. He means Kp equal to 1000. If somebody told me that we are having a system with Kp equal to 1000, what can I understand out of this? That's why we are studying the constants and we are studying the case in this way. Now I hope you will get very clear about it. Somebody told me Kp equal to 1000. What will I understand? First of all, I will understand that the system is stable, because steady state error to be applied to a stable system. So if there is finite error or finite of the constants, the system is stable. So when he tell me there is a Kp, it's not infinity, that means the system is stable. The other thing, the system is type 0. Why? Because Kb give me finite. Kp give me finite. That means the system is type 0. This is the other idea. Okay. The input test signal is is step input. Of course, to get this one, the only signal will give me finite error for the system. Let's say something like this. So the signal sent here for the transfer function, which I don't know what is it, but I know that it's zero type, means having no integrator. The only input will give me finite error is going to be the step. This is another idea we are getting from this value. And finally, he said the error per unit is per unit step is, we can calculate, it's not continued here, I will continue it, no problem. The error can be calculated as 1 over 1 plus Kp, which equal to 1 over 1 plus 1000, which equal to 1 over 1001. So I can also calculate the error. See, all of these information is come to my mind once I know that Kp equal to 1000. This example is a design example. Means we need to design the system for a specific steady state error. That's why he keep K here. This K is the value which we need to calculate to get the required steady state error. Let us read the question together and you will see how. Give the control system below, given the system, control system below, find the value of K so that there is 10% error in the steady state. So the steady state error equal to 10%. Steady state error equal to 10%. 10% means 10 over 100. So we need to calculate the value of K which is going to maintain this steady state error. How to consider this? He's saying here, observe that the system is negative feedback. Observe the system is type 1. System is type 1. Why it's type 1? Because the steady state error going to be if the input is ramp. If the input is other than the ramp, there will not be steady state error. Will be either 0 or infinity. But with type 1, we are going to have a steady state error only if the input is ramp. So I figure out now how the input going to look like. For the type of system, you see here he's saying only ramp is a producing error, which means this 10%, which equal to 0.1, as I said, 10 over 100, is equal to 1 over kV, because we know that kV is the constant for ramp. kV is the velocity constant, or the constant for ramp. The error for the, in case of ramp, we said it's equal to 1 over kV. That means whatever value he gave me is equal to 1 over kV. That's very fine. Now, kV found to be 10. Now, if I want to calculate the value of kV, it's equal to the limit of S into GS. That means 10 is equal to S into limit of S into GS, which to be equal to, the 10 is equal to S into GS. Notice that S will cancel S. The remaining is going to be this function, which equal to 5K over 6 into 7 into 8. That means 10, the 10 which the kV which we found earlier equal to 5K over 6 into 7 into 8. From there we can calculate K equal to 672. That means the value of K to get the specific error of 0.01 or 10% is equal to 672. Another example, he's saying a unity feedback system has the following forward transfer function. We know what is forward transfer function. Find the value of K yield to a 10% error in a steady state. Means the steady state error, we want it to be 10%. So it's the same style. Type of system is 0 this time. system is type 0, that means only finite error will be when the input is a step. And the formula for the finite is going to be 1 over 1 plus Kp, which means the 10% is equal to this value. You see 10%, which equal to 0.1 equal to 1 over 1 plus Kp. From there, we can calculate Kp to find that it's 9. Kp is equal to 9. And from that constant equation, Kp is equal to the limit of Gs. That means 9 is equal to the limit of Gs, which means 9 is equal to 12K over 14 into 18. From there, we will find K equal to 189. That's how we can calculate the gain or the constant, which is going to give me a specific steady-state error. I hope it's clear, my dears. If you have any question, keep it until we meet in the discussion session. Thank you.